Okay, so picture this. You're sliding a window open during a rainstorm. The faster you slide it, the more rain the opening catches, right? Now, what if that rain was actually a magnetic field? As you slide a conducting rod, that's our window frame, the area it sweeps out gets bigger. That means it catches more magnetic flux. And thanks to Faraday's law, that change in flux creates a voltage. That, my friends, is motional EMF. It's all about motion creating electricity.
Now, this isn't just some neat physics idea, you guys. This is a high-stakes exam classic. The people setting the exams absolutely love asking you to prove the result using two completely different methods, and they'll give you a full 5 marks for it. So today, that's what we're going to do. We're going to conquer both methods step by step so you can walk in there and claim every single one of those marks. All right, section 1, the 5-mark challenge. Before we even touch the math, we've got to understand the physical setup. This is the classic scenario you're going to see in pretty much every textbook and on every exam.
So here it is. This slide lays it all out. We've got a conducting rod of length L, that's the sliding edge of our window. It's moving with a velocity v on 2 parallel rails. And the whole thing is sitting in a uniform magnetic field B, which those little X's show is pointing into the page. That's our magnetic rain. As that rod slides, the area of the loop gets bigger and bigger, catching more and more of that magnetic flux.
Okay, let's dive into section 2. This is method 1, what I like to call the big picture view. For our first approach, we're going to look at the whole system from a bird's eye view, using Faraday's law of induction. It's all about the total change in flux.
All right, let's walk through these steps. It's super logical. Check it out. In a tiny little bit of time, dt, the rod moves a tiny distance, dx. This motion sweeps out a new little sliver of area, dA. So the change in magnetic flux, d phi, is just the strength of the B field times this new area. Now, here's the magic moment. We plug this right into Faraday's law. The induced EMF is the rate of change of flux. And would you look at that? The dt on the top and the dt on the bottom cancel out perfectly. We're left with this beautiful, simple result. The EMF is just B times L times V. Done.
But wait, a voltage has to have a direction, right? Which way does the current actually flow? Well, for that, we pull out our trusty tool, Fleming's right-hand rule. As you can see, you just point your thumb in the direction of the motion, your forefinger in the direction of the field, and boom, your middle finger tells you exactly which way the current wants to flow. It's that simple. All right, on to section 3. This is method 2, the microscopic view. We got our first 2.5 marks with the big picture approach. Now, let's zoom way in for the other half. Instead of looking at the whole loop, we're going to focus on the individual charges, the free electrons, just inside the metal rod itself as it's moving. You know, this approach is so cool. Think about it for a second. The rod is moving, right? That means all the free electrons floating around inside it are also moving with velocity v through that magnetic field. And we know from the Lorentz force that a moving charge in a B field feels a force, F equals QVB. This force literally shoves the electrons down to one end of the rod. As they pile up, an electric field builds up, pulling them back. Eventually, you hit this perfect balance, an equilibrium, where the electric force pulling them back equals the magnetic force pushing them down. And when you calculate the voltage created by that electric field across the length of the rod, you get BLV, the exact same answer. And this right here is the moment that should give you goosebumps. Seriously, we just used two completely different ways of thinking. One was about the changing area of a big loop. The other was about the forces on teeny tiny little electrons inside a wire. And they both led us to the exact same place. This is what makes physics so powerful. It's consistent. I mean, just look at them side by side. On the left, the big picture view using Faraday's law. On the right, the microscopic view using the Lorentz force. Two totally different paths that lead to one identical truth. It's a perfect check on our understanding. So there it is, the big takeaway. Doesn't matter which physical lens you use, the induced EMF is BLV. You've now got two complete, valid derivations in your toolkit to lock in those full 5 marks. Okay, so knowing the formula is half the battle, but applying it when the pressure's on, that's another story. Examiners just love setting traps for us. So let's apply our knowledge to a typical exam question from the source quiz and see how to dodge them. So here's a classic problem. Take a look. You've got the length, 20 centimeters, the velocity, 10 centimeters per second, and the field, 0.5 Tesla. All the ingredients are there. So what's the very first thing you do? Just take a second and think about it.
If your brain immediately screamed, "Convert the units," then you are absolutely on the right track. That is the #1 trap. This formula only works in SI units, meters, meters per second, and Tesla. If you use centimeters, your answer is going to be way off. The second trap is to check for perpendicularity. The problem says it's perpendicular, so we're good. But if that rod was sliding parallel to the field lines, it wouldn't cut any, and the EMF would just be 0.
So yeah, step one, always, is to just lay out your variables and get them into the right SI units. No excuses. 20 centimeters becomes 0.20 meters. 10 centimeters per second becomes 0.10 meters per second. The B field is already in Tesla, so that's fine. Now we're ready to plug and chug.
And once you've done that, the calculation is a piece of cake. Look, EMF equals 0.5 times 0.20 times 0.10. That gives us 0.01 volts, or 10 millivolts. By just taking that one extra step to check our units, we nail the correct answer.
But hold on, we're not quite done. Motional EMF isn't just about voltage, it's this beautiful, perfect example of energy being converted from one form to another. For those longer, beefier questions, like Q15 in the source quiz, you need to get the full picture, how force, power, and energy are all tied together.
This table really shows how it all flows together. Once you've got your EMF, bang, you can get the current with Ohm's law. From there, you can find the power being turned into heat in the resistor. But here's the really crucial bit that brings Lenz's law back into play. That current flowing in the rod, inside that magnetic field, creates a magnetic force that fights your motion. It acts like a brake. So to keep the rod moving at a steady speed, you have to constantly push it with an external force.
And that leads us to this amazing conclusion. If you calculate the mechanical power you're putting in, which is your pushing force times the velocity, it turns out to be exactly equal to the electrical power being dissipated as heat in the resistor. It's perfect energy conservation. The work you do pushing the rod is perfectly converted into electrical energy and then into heat. Nothing is created or destroyed.
So, to sum it all up, motional EMF is just Faraday's law and Lenz's law working together in perfect harmony. You've got two solid derivations, you know the common exam traps to sidestep, and you understand the deep energy conservation principle that's really going on. You are totally ready for any motional EMF question they can throw at you.
But this brings up a really interesting question. We've seen how a circuit can oppose external motion. But what happens when a circuit opposes a change in its own current? What creates that opposition? Well, that phenomenon is called self-inductance. It's basically electrical inertia, and it's exactly what we're going to break down in our next explainer.